Hi everybody, it's Mrs. Dinkelman again. This is Unit 8 and the section is summation notation. There's a couple reasons I want to go over this. We are going to be learning about series in, I don't know, a few units. And so we just want to kind of remind us about summation notation. And the other thing is this is something we tend not to teach in AB. There are every once in a while a couple questions that have to do with this and Riemann sums. But it's something that we just usually don't teach. So I thought I'd sneak it in a little bit here in the BC class. So this sigma notation, just a quick reminder about it, is just helping us add a bunch of things together without having to write them all out. So if we just kind of do a couple of examples to remind ourselves, something you probably did in pre-calc or even earlier, to remind us what we're doing here. So remember, these always go by integers. So this is going to be n equals 1, 2, and then stops at 3, and then we add all those together. So we're going to do 1 over 1 plus 1 over 2 plus 1 over 3, and we would figure out what that equals. Sometimes, and we're going to go through this a little bit more when we get to the later sections, is we're going to have to write things in sigma notation. So there's a couple ways we could do it. I'm going to go with let's see, let's just do n, and I'm going to start with n is 1, and then we're going to end at 6. There's, again, a couple other ways that we can do that. So what we want to try to do is think about how a Riemann sum, so adding up all those rectangles, could be written in sigma notation. So right here I have a picture of the square root of x, and we're finding the area from 0 to 3. And if we only had to do a few rectangles, like maybe 3 or even 6 rectangles, we could probably do that by hand. But what if we were asked to do it using 30 rectangles? And we're going to just, for the sake of keeping it and being like the AP exam, thinking about a right Riemann sum or using the right endpoints. So we want to think about how we could write a formula there. And I have it written down here. So we would really start with the 0 here. And maybe this picture doesn't quite capture exactly what I want, but the idea that we have just a lot of rectangles here. So our delta x, let's think about that. So we're going from 0 to 3. And so if we do our b minus a over n, so that delta x, again, being the width of each rectangle, so delta x, I'm just going to write that formula again. I tend not to really think about that formula, just to know I'm going from 3 to 0, and I'm going to have to divide that into 30 rectangles, so a tenth. And I did a little bit here, having it not simplified at first and then simplifying. So what we would do here, here's our delta x, that 1/10, and I simplified it in kind of this next side of the equal sign. And since we're doing the right rectangles, our first would be that 3/30ths, and then we would keep adding 3/30ths to get where we were getting. And again, we can simplify that a little bit. And then since we're doing the right Riemann sum, the very last thing that we would take would be at that 3 level, so 30/10 technically. So if we try to write that using sigma notation, what we can see here is that we have this 1/10. Again, that's the width of every single rectangle. And then we have to try to figure out how we can plug things in to that function and make sure we get all 30 of those rectangles. So you can see here I went from 1 to 30. I'm using I here. We tend to use I and not n, because n is usually the number of rectangles. This is not imaginary I, it's just something that we kind of choose to use with that sigma notation. So then we can kind of keep thinking about how this might look if we had 300 rectangles. So let's just kind of compare the difference. I won't necessarily write everything out. If we had 300 rectangles, then my delta x would be 3 over 300, or 1/100th. Okay, so think about how that would look. So instead of 1/10 here, 1/100th, and then we would kind of continue going by 1/100th every time until we got to 300 over 100. So again, sigma notation can be really helpful if we wanted to do that many. And just kind of a by the way, and especially since I have this calculator out here, we can do sigma notation on our calculator. So if you go to the calculus menu, which is really the F3 tab, you can see here that there's a sum, so sigma, and then it's called sum. And we could actually put that in here. We could go 1/10 times, let's see, square root, and pick a variable. It doesn't really matter. I'm just going to pick x because it's really available. So instead of an I there, so square root of x over 10, comma, I think we have to put an x, but let's just see. x, and then we're going to go 1 to 30. We'll see if I need that x in there. It'll let me know if it's upset with me. And it's maybe going to take a minute because that's a lot of rectangles and things to add up and to try to figure out what's going on. Okay, so we'll just kind of leave that set to the side and make sure it works here in just a minute. Okay, so what we really want to try to do and what we really need to know is that when we're doing an integral, we're really doing an infinite amount of rectangles. And so this was the original how we figure out what integrals really are, is that it's a limit of a sum that's an infinite amount. And so instead of using the sigma for a big summation, we use that big S to mean that we're summing up an infinite amount of rectangles. It turns out that we don't have to work that hard because we figured out the antiderivative. So we know how to get that fairly easily, but that's technically what the integral is doing. So if we're going to do that, again, think about what delta x is going to be. Delta x, b minus a, over the number of rectangles. So n for now, because we want n to be infinite. So we're going to put an infinity in there earlier. And if we kind of come up here and think about what this looked like, okay, so we kind of use that delta x in here, this 1/10, because we keep going by 1/10 every time, or again 3/30 if we think about it that way. So you can kind of compare what's happening with this one to looking at 3 over n as our delta x, and then we're going to use that I to keep getting more y coordinate things. Okay, I'm just going to quick peek at the calculator and see if it's done. Nope, it's still busy. We'll go back and look. I can try something different if we need to. Okay, well, same function, but let's say we're going from 1 to 4 and we want to do 30 rectangles. So it's going to be a little bit different because our first data point doesn't start from 0. So the first thing we're going to use is 1 plus that 1/10 so that we can pick that right-hand limit. So you can kind of see in some cases that we have a little addition in here. Now it could technically be that our function was the square root of 1 plus x. That could also be, that would be our same function shifted over a little bit. Or it could be that we just wanted to start in a different location. So these aren't always easy. Again, they happen on the AP exam rarely, but we just want to get a good practice with them. And I'm going to give you some advice on finding them. Okay, so let's talk about this example 3. Again, let's talk about what's happening with delta x. And we're trying to rewrite the integral. That delta x is really terrible. Let's try again. Okay, so delta x is going to be b minus a divided by n. Okay, so we're going to see that happen in our sigma notation. So we're saying we want there to be an infinite amount of rectangles in this sigma notation. So we usually start with I equals 1 to n, because n will eventually be infinity. 2 over n is our delta x, so each of our rectangles is going to have that height. That's the way I like to think about it. You'll see here in example 4, they put it on the other side, so just be careful about that. And then we're going to want that delta x to be plugged into that x squared there. So maybe I should put brackets here. So I'm going to leave a little space here because I know it's going to be that delta x squared plus 1. Okay, but I don't want to just use that same 2 over n every time. I want us to keep getting bigger and bigger as far as moving along the x-axis a little bit. So this is where we're going to plug in our I so that we can make sure we still go by increments of 2 over n, but we might do 2 over n and then 4 over n and then 6 over n and so on. And we would plug that into our function to figure out how tall our rectangle is. So that's what the sigma notation looks like. Oftentimes we have to do the reverse. So now we're trying to find the integral. So I always like to identify what the delta x is. So the delta x here is 3 over n. And that's kind of one of the things that I just substitute into my problem. So I can see that delta x, that's actually where my x is going to go. So I claim that our function is, we could do it a couple ways. Our function could be sine of 5 plus x dx. And now we have to figure out from where to where, okay? So one of the things I like to think about is what happens with the ending points here. So if we're starting here and that 5 is as part of our function, then our first delta x must have been just shifted over from that. So it must have been from 0, and there's lots of ways to think about how that's going to work. And then I also like to think about if I take that delta x out of there what I end up with at the end. And maybe I should think of it this way. So if I have b minus a over n here, and I've decided that my a value is 0, then I know my b value is 3. So this is one option. That's kind of why these don't turn up on the AP exam a lot, because there's lots of different ways to write what's happening here. Another option would be saying, I think this thing starts at 5 because of that 5 that's right here, okay? Thinking a little bit like what happened with this picture right here. We started at 1 because that's what was happening in there. In that case, then, our function doesn't include the 5. It's really just sine of x dx. Oops, I don't know why that shift happened. Okay, so let's find the other endpoint then. Again, thinking about this separately, we know that delta x is 3 over n. We think in this case that we have a 5 here. And so now we have to figure out how to get a 3 on top here. So that looks to me like it might be 8. So these two would calculate as the same thing. And that's really just because sine x and sine of 5 plus x is really just the same function, just shifted over. So that's why our limits have been shifted over as well. Okay, so just give it a shot. Again, if you're feeling frustrated, just remember that in your mind there might be one on the AP exam. It's just worth kind of trying and getting a few under your belt, and then maybe they'll become easier and easier.